The beginning of the Chapter 1, Section 7 notes just talks more about derivatives, and we're going over the notation once again. And now they're changing the variable from x, which is what we normally have, to a variable like t. So you can see just by looking at this that nothing really changes other than the variable, but you've got to abide by the new variable. So for example, if they tell you to take the derivative with respect to t of t squared, that's not going to be 2x, that's going to be 2t. And we can either write it this way, which is with the Leibniz notation, we can write it this way, which is prime notation, or we can write it this way, which is dy dx, but because it's t, it's dy dt. So make sure that you are familiar with all three notation types. So where would you come up with dy dt? That would be if the previous step had been y equals t squared. So your function is going to be presented as y equals t squared. If that's the case, you can write dy dt is, and then take the derivative using the power rule, 2t. If they said instead with function notation, f of t equals t squared, then you would say f prime of t equals 2t. So you can see from both diagrams that clearly the functions look exactly the same. The only difference is now you're going to have t be your variable and not x. So just be flexible with the variables. Be aware of them, know how to handle them, don't be intimidated by them. And the three types of derivative notations you want to be aware of and know how to handle well each time, because notation is very, very important in calculus. So on the bottom of the first page of the notes, we say that you can use the same rules of derivatives over and over and over again. So you can take the second derivative, the third derivative, the fourth derivative, etc., just by using the same derivative style and technique. So look right here in this box. If my original function f of x equals x to the fifth, f prime of x is f prime of x is 5x to the fourth. F prime prime, take the derivative of f prime to get f prime prime. And I'm just going to use the power rule over and over and over again. So that's how we would do prime notation for multiple derivatives. What if we had Leibniz notation? What would that look like? So that's going to look like your orange box right here. So if your notation is d dx, if I want you to take the second derivative using Leibniz notation, this is how I would write it. D squared over dx squared. Notice where I have the power of 2, and make sure that you are doing that correctly, because you don't want it on the d in the denominator. You want the power to be on the variable in the denominator. So look at that carefully and be aware of it. And the third type of notation that we would use to take multiple derivatives is going to be the notation in the bottom of the box. Right here, if I want you to take the second derivative and I'm using dy dx, I would tell you that I'm having you give me the answer and you present it as d squared y dx squared. So in both Leibniz and the other dy dx notation, notice where the squared terms go and make sure you do that correctly. I'm going to do a fourth notation, so I'm going to write over what I just did. Here is really a fourth notation. So we have 4 colors, 4 notations. This notation, when using the notation y equals f of x, you are allowed to use that prime notation on the y. So for example, if y equals 7x squared, I could say y prime equals 14x, and that's also a prime type of notation. So the y prime and the f prime of x are very similar in their design. So be aware of all the notations, be able to recognize them, and be able to apply them correctly. Because notation is the way we communicate in math, I want to point out yet another type of notation so that you can understand what it means. So when evaluating a derivative at a specific value of x, say at x equals a, we get a number f prime of a that gives the slope of the curve y equals f of x at the point a f of a. Another way of writing f prime of a is this. So for example, if they tell you that y equals 8x squared, and then they write dy dx, they want you to find dy dx and evaluate it where x equals 2. What does that mean? So this line means evaluate it at. Okay, so I would say, okay, dy dx, following the notation that they've chosen, equals 16x, and if I evaluate it at x equals 2, then I put a 2 where I have my x, and that's going to equal 2 times 16 is 32. All right, so that's the notation and what it means. So it's just evaluate it at. You also could say d dx, evaluate a derivative at x equals 2 of 8x squared, and in that the case, you would just say that equals 32. Notice that I went from having dy dx notation to d dx notation, and because I switched to d dx notation, it was followed by the function. When I used dy dx notation, it's followed by the equal sign, and then that equals the derivative. So just be aware of what the notation means and use it correctly. Okay, this section of the textbook talks about marginal cost, and we have already addressed this, but for completion or completeness, I wanted to put it in the notes as well. So marginal cost is just C prime. It's the slope of the cost function. It's the change in cost at the margin. So if I give you C of x equals, and I ask you for the marginal cost, you need to recognize that that means C prime of x. So C prime of x is marginal. And don't expect me to explain that when I ask it on a test or a quiz. If they say find marginal cost, you need to know it means C prime of x. Or if they ask you to comment on marginal cost and they give you C prime of x, you need to recognize what that is. Similarly, for marginal revenue and marginal profit, they are all prime notation. They are all the first derivatives of their individual functions. So marginal revenue is the first derivative of revenue. Marginal profit is the first derivative of profit. It's the change in profit. It's the rate of change. It is the slope of the profit and the revenue functions, respectively. So that should all be familiar. I just have it here again for completeness. Okay, this little feature on your calculator is going to be an important thing for you because we will eventually start looking at graphs that have the derivative of a function as well as perhaps a second derivative. So there are two ways to do this on your graphing calculator. The first way is you can just put your function, take your first derivative, that's your y2 then, and then your y3 is your second derivative. So this was y, this was y prime, this was y prime prime. Or you can have the calculator do it for you. Now, when you have the calculator do it for you, it will not give you the equation that would be your first derivative. It'll just plot it for you. So this n derivative is under math. And when you do the n derivative, you then tell it to take the derivative of y1 of x, and it's going to be in terms of x, and you're going to put it in your y2. So your y2 graph will be the first derivative of y1. Your y3 graph, you will tell it to look at y2 instead. You get the n derivative, so n derivative is found under math, so look for it there, and then your y1 and your y2 is found under under VARs. Okay, so let me just, is found under VARs on your calculator, and then you go y VARs and then you select it, and you've done that in other classes. But this is a notation that you would have to do if you want your calculator to just go ahead and plot the second derivative, the third derivative, whatever derivative you want of your function. It's a building process. All right, I talked to you about trig in the past, and we know that there's trig in calculus, so I'm going to have you start memorizing some things. In the next couple of classes, we will address trig more specifically, but I want to at least give you a brief insight into what the derivatives of the common trig functions are. So, first off, the derivative with respect to x of sine of x will be, and this is for you to memorize, cosine of x. The derivative with respect to x of cosine of x is going to be negative sine x. And the derivative with respect to x of tan x is going to be secant squared x, and that's secant. Alright, so you need to memorize those. We're going to derive them for you. I've already done a little bit of talking about the derivative of sine being cosine, but we'll do it more explicitly. So one more time, the derivative with respect to x of sine x is plain old cosine x. The derivative with respect to x of cosine x is negative sine x. And the derivative with respect to x of tan x is secant squared x. Okay, so memorize that. Now we're going to go on to some other problems involving this. So as you can imagine, that chain rule is going to apply to trig as well. So if the angle, so the angle is what follows the trig word, if that angle is not just x, the chain rule has you take the derivative of the angle as well. So, for example, if I do this problem right here that I have first, my answer will be, and I'll tell you, well, let's do it this way. If my function was sine 3x, okay, and this 3x is my angle, my derivative is going to be, the derivative of sine 3x is cosine 3x times the derivative, so take the derivative with respect to x, of the angle itself. So therefore, my derivative will be, this is going to be 3 right here, so I can bring the 3 in front, 3 cosine 3x. Okay? That's what that derivative is going to be, because not only did I take the derivative of the trig function, I then took the derivative of the angle. Alright, let's do the next one. So I'm going to erase this one, and we'll do the next one. And what we'll do is I'll just put the answer up there. So it was 3 cosine 3x. Okay, let me try that again. Okay, so this is 3 cosine 3x, and the 3x is the angle. Alright, so let's do our next problem, which is going to be the derivative of cosine 2x squared, and that 2x squared is my angle. So if my function equaled cosine, and I'm going to use parentheses so that you can really see what the angle is, then my derivative would be, the derivative of cosine, remember, is negative sine, don't change your angle ever, times the derivative of the angle. That derivative is going to be 4x. So my final answer, bringing the 4x in the front, will be negative 4x sine, again, I haven't changed my angle, 2x squared. If you find you change your angle, something is wrong. Okay? So the next problem we're going to do is the tan problem. So I'm not going to write my answer up there, so we'll just revert back to that. So let me look at the tan one now. Now, think about, as I'm doing this, what's the derivative of tan? Hopefully you're saying secant squared. Okay, now make this tan. There we go. Okay, so now our function is going to be tan of 3x squared plus x. That's my angle, so my derivative will be secant squared. Don't change your angle, times now the derivative of the actual angle. So the angle always comes along with the trig term, just the way it is. That derivative is going to be 6x plus 1. So my final answer will be 6x plus 1 secant squared, and then 3x squared plus x. There you have it. So now you can see how you can use the chain rule. Now, fun times, you can use the chain rule twice with trig, and we'll talk about that in the next problem. Alright, so the power rule, when you have trig, you want to be careful about writing and understanding a problem. We tend to write squared trig terms by squaring just the word of the trig, not putting it in parentheses and then squaring the whole term. When we write this first box, we really mean this. And if we're going to take the derivative correctly, it is in absolutely our best interest to write it this way. And this is why. The chain rule is going to come into effect. And so if I want to take the derivative of that, so I'm not going to use this right here, because I'm going to move this down. So if I know that my f of x, writing it correctly, or writing it so that I can see exactly what I'm doing, if that is my f of x, and that's my angle, then my f prime of x is going to be obtained by using the power rule first, right? And then this is raised to the first power, and then times the derivative of what's inside. So I need to take the derivative with respect to x of cosine x. So my answer will be this derivative. So what if I said f of x equals, and we'll make it sine squared 3x. Now, that's a dangerous way to write it, so I'm going to write it this way. Notice I haven't changed the function to a first derivative. I'm just writing it so that I don't make an error. Okay, here's your chain rule. Power rule first, 2, exactly what I see, don't touch anything inside, to the first power, right? Now take the derivative of this, which is going to be cosine 3x, and then take the derivative of this, which is 3. So I didn't write the ddx notation because of space here, but at the end of the problem, your answer is 6 sine 3x cosine 3x. And the big takeaway here is that I want you to notice your angles never change. So if you find that your angle ends up being 3, you know you've done something incorrectly. Whatever angle you came in with, which was 3x, has got to be the angle that you leave with. And we have it two places here, but it is the same angle. Okay, so that's the notes for this section.